Venus's atmospheric chemistry in ways we're only beginning to understand. This isn't science fiction. This is November 2025, and it's happening right now while you're watching this. Venus's upper atmosphere is currently processing chemistry that arrived from beyond our solar system just weeks ago. The cloud layers that have remained essentially unchanged for billions of years are now circulating molecules that have never been part of Venus's natural system. And unlike Mars, where materials deposited on the cold surface and waited for excavation, Venus's chemistry is active, transforming, reacting, exploring new pathways immediately. But before we understand what this means, we need to establish exactly what happened on November 3rd. The interstellar comet 3I Atlas, the same object that passed Mars on October 3rd, made its second close approach to an inner solar system planet. The distance was 0.65 astronomical units, roughly 97 million kilometers. That's close enough for Venus's gravity to capture material from the comet's coma. That's close enough for the thin envelope of sublimated gas and dust surrounding the comet's nucleus to intersect with Venus's upper atmospheric layers. That's close enough for an exchange of materials between an interstellar visitor and a planet that hasn't received external chemistry in eons. The timing matters more than you might realize. When 3I Atlas passed Mars on October the 3rd, Mars presented a thin atmosphere and a cold, inert surface. Materials arrived, settled, and essentially froze in place, waiting. But Venus is different. Venus has an atmosphere 93 times more massive than Earth's. Venus has wind speeds in the upper atmosphere reaching 100 meters per second, creating a global superrotation where clouds circle the entire planet in just 4 Earth days. Venus has temperatures at cloud level ranging from 0 to minus 60 degrees Celsius, cold enough for chemistry to occur, warm enough for reactions to proceed. And most critically, Venus has sulfuric acid clouds that are both incredibly corrosive and paradoxically capable of preserving certain organic molecules we never expected to survive there. When 3I Atlas swept past Venus, its coma extended millions of kilometers into space. The exact composition varied with distance from the nucleus, but as we established from the Mars encounter, the comet was actively ejecting specific materials, water at rates exceeding 120 metric tons per hour, hydrogen cyanide at approximately 80 grams per second, carbon monoxide at similar rates, and something nobody predicted: spectroscopic evidence suggesting unusual nickel enrichment relative to iron, with the exact separation mechanism remaining uncertain. Venus's gravitational field captured a fraction of these materials. Not all of it, most escaped into space, or was deflected by solar wind, but enough. Estimates suggest somewhere between 3 and 10% of the nearby outgassing material intersected Venus's gravitational and atmospheric capture zones. Here's where the geometry becomes critical. Mars's encounter was partially glancing the comet's trajectory swept past Mars at an angle that limited direct interaction time. Venus's encounter was more favorable. The comet's path placed Venus closer to the outgassing stream's center. The materials arriving at Venus weren't just the diffuse outer edges of the coma, they included denser concentrations from regions closer to the nucleus. This means higher concentrations of everything: water, hydrogen cyanide, organics, metals arriving at Venus compared to what Mars received. And unlike the Mars encounter, which had multiple spacecraft from different space agencies positioned to observe and create redundant measurements, the Venus encounter was documented primarily by a single spacecraft, JAXA's Akatsuki orbiter. This creates a limitation we need to acknowledge immediately. NASA's Parker Solar Probe was in a different part of its orbit during the encounter. ESA's Bepi Colombo, traveling toward Mercury, wasn't positioned for detailed Venus observations. Akatsuki recorded data during the encounter window, and that data has been transmitted back to Earth and is currently being analyzed. But we don't have the multi-spacecraft verification that made the Mars observations so robust. Our understanding of what actually happened depends more heavily on interpretation of limited data, on models that predict how Venus's atmosphere should respond, and on the chemistry we know must occur when these materials meet Venus's clouds. What we know with certainty is this: 3I Atlas passed Venus at a distance allowing material transfer. The comet was actively outgassing at rates consistent with its late October activity levels. Venus's atmosphere, being thick and gravitationally bound, would capture a measurable fraction of that material. The upper atmospheric layers would be the first point of contact where incoming molecules collide with atmospheric gases and begins slowing down, integrating into Venus's circulation patterns. What we don't know yet, what the data currently being analysed will tell us, is the specific concentration at which materials arrived, the exact chemical pathways they followed once integrated into the clouds, and the atmospheric system's immediate response. But here's what makes this encounter fundamentally different from anything Venus has experienced in geological timescales: external chemistry. Venus's atmosphere operates as a closed system. The materials circulating in those sulfuric acid clouds come from Venus's surface, Venus's geology, and Venus's ongoing photochemical processes driven by solar ultraviolet radiation. Nothing arrives from outside. The system is in equilibrium with itself. Every molecule that rises from the surface eventually returns. Every photochemical product eventually recombines or breaks down into components that feed back into the cycle. Venus's atmospheric chemistry has been running the same loops, the same reactions, the same pathways for billions of years. Stable, predictable, isolated, until November 3rd. The materials 3I Atlas delivered aren't in equilibrium with Venus's existing chemistry. They're foreign, reactive, and they carry information chemical structures and elemental compositions from environments completely unlike anything Venus has experienced since its formation. Hydrogen cyanide, for example, doesn't occur naturally in Venus's atmosphere in significant quantities. When it arrives from the comet, it represents genuinely new chemistry. Water vapor, while present in Venus's atmosphere in trace amounts, arrives from the comet in concentrations that temporarily elevate local humidity. Refined nickel, which should not exist in Venus's clouds at all, suddenly becomes part of the atmospheric mix, carried in dust grains, and potentially dissolving into sulfuric acid droplets. These materials don't sit passively once they arrive. Venus's atmosphere is too dynamic for that. Within hours of arrival, atmospheric circulation begins distributing the materials horizontally around the planet and vertically through the cloud layers. Within days, photochemistry begins transforming the molecules. Solar UV radiation breaks chemical bonds, creates reactive radicals, drives reactions that wouldn't occur in darkness. Within weeks, the entire atmospheric system has been exposed to and begun processing these foreign materials. Venus's chemistry, so stable for so long, has been perturbed. The system is responding. And right now, in late November 2025, that response is actively unfolding in Venus's upper atmosphere. The question isn't whether Venus changed, it did. The question is what Venus is doing with the chemistry it received, how long the changes persist, and whether anything unexpected emerges from the interaction between sulfuric acid clouds and molecules from interstellar space. That's what we're about to explore, and the implications reach far beyond Venus itself. To understand what 3I Atlas just disrupted, you need to understand what Venus's atmosphere actually is beneath the simplified descriptions we usually hear. Yes, it's hot. Yes, it's acidic. But Venus's atmospheric chemistry is far more intricate than hellish wasteland suggests. And that intricacy is precisely why the introduction of external materials matters so profoundly. Venus's atmosphere isn't a single uniform layer of sulfuric acid and carbon dioxide. It's a vertically stratified system with distinct chemical zones, each operating at different temperatures, pressures, and compositions. Think of it like an ocean. With layers, the surface waters are different from the thermocline, which is different from the deep ocean. Venus's atmosphere has similar stratification, and when materials from 3I Atlas arrived, they didn't interact with one uniform environment. They encountered multiple chemical zones simultaneously, each responding differently. Start at the top, where the comet's materials first make contact. The upper cloud layer extending. At these altitudes, temperatures hover around 0 to minus 20 degrees Celsius. Cold enough for water to condense into ice crystals. Cold enough for certain organic molecules to remain stable longer before photochemistry destroys them. The atmospheric pressure here is low, about 1/10 of Earth's surface pressure, which means molecules have longer mean free paths before colliding with others. This is important because reaction rates depend on collision frequency. Lower pressure means slower reactions, which means molecules persist longer. This upper cloud layer is also where most of the atmospheric mixing happens. Winds driven by temperature gradients and pressure differences create circulation patterns that redistribute atmospheric contents around the planet every 4 Earth days. Materials arriving here don't stay localized, they're immediately caught up in circulation and begin spreading globally. Drop down to 50 to 60 kilometers altitude, and you enter the middle cloud layer. Here, sulfuric acid concentrations increase to 75 to 90%. Temperatures drop further to -20 to -40 degrees Celsius. This is where most of the visible atmospheric features occur, the Y-shaped patterns and vortices that spacecraft cameras capture when imaging Venus. The middle cloud layer is denser, the chemistry more aggressive. Molecules that survived in the upper layer begin encountering higher acid concentrations here. Some break down, some transform into different compounds, some incorporate into the acid droplets themselves, becoming part of the liquid solution rather than remaining as separate gas phase molecules. Below that, 45 to 50 kilometers altitude, lies the lower cloud layer. Sulfuric acid concentrations reach 80 to 90%. Temperatures are -40 to -60 degrees Celsius. Pressure is approaching 1 Earth atmosphere, and the environment becomes increasingly hostile to organic chemistry. This is the zone where most molecules that survive the upper layers finally break down or transform into stable end products. The lower cloud layer acts as a chemical terminus for many atmospheric processes. Materials that make it this deep are either incorporated into precipitation that eventually returns to the surface, or they're broken down into components that rise back up through convection to begin the cycle again. Beneath all three cloud layers, from 0 to 45 kilometers altitude, lies what's optimistically called the clear atmosphere, though clear is misleading. Visibility is limited by hazes and aerosols. The atmosphere here is dominated by carbon dioxide and nitrogen, with temperatures increasing dramatically toward the surface. By the time you reach Venus's surface at 460 plus degrees Celsius, chemistry operates under conditions we'd recognize from industrial furnaces, not planetary atmospheres. Materials don't survive here, they're incinerated, decomposed, or absorbed into surface geology. Now, why does this layering matter for our story? Because when 3I Atlas's materials arrive, they don't all end up in the same chemical environment. Lighter molecules like water vapor and hydrogen cyanide gas penetrate deeper into the atmosphere before atmospheric drag fully decelerates them. Heavier particles, dust grains containing nickel, silicates, and other minerals decelerate faster and remain in the upper atmospheric layers longer before settling. Each type of material encounters different chemical conditions based on where it ends up in this stratified system. Water arriving at the upper cloud layer meets dilute sulfuric acid and cold temperatures. It condenses, forms mixed droplets, and releases heat. Hydrogen cyanide arriving at the middle cloud layer dissolves into more concentrated acid and begins hydrolyzing, breaking down into ammonia and formic acid through reactions with water molecules in the acid solution. Nickel-containing dust grains, when they encounter sulfuric acid at any level, react to form nickel sulfate compounds that dissolve into the droplets, becoming part of the liquid phase. Each material follows its own pathway through Venus's atmospheric chemistry. Each transformation creates products that themselves have chemical identities and behaviors. And all of this happens within a system that's been running essentially unchanged for billions of years. Venus's atmospheric chemistry operates as a conveyor belt. Sulfur dioxide rises from the surface or is produced through photochemical reactions in the lower atmosphere. Solar ultraviolet radiation breaks it down in the upper atmosphere, producing sulfuric acid through reactions with oxygen and water. The sulfuric acid condenses into droplets, forming the cloud layers. Those droplets grow, coalesce, and eventually precipitate downward, though on Venus, precipitation doesn't reach the surface. The intense heat in the lower atmosphere causes the droplets to evaporate before they can fall all the way down, releasing their sulfuric acid back into gaseous form. The sulfur dioxide regenerates and rises again. The cycle repeats. This has been happening for eons, creating the stable sulfuric acid cloud layers that define Venus's appearance and chemistry. The system is in equilibrium because it's closed. Every component comes from Venus itself. Every reaction product eventually feeds back into the system. There are no external inputs, no asteroids delivering water, no comets injecting organics, no meteorite flux bringing metals. Venus's atmosphere is isolated from external influence, operating purely on its own internal cycles and solar energy input. This equilibrium creates predictability. Scientists studying Venus know what to expect in the clouds: sulfuric acid droplets, trace water vapor, carbon dioxide, sulfur dioxide, some carbonyl sulfide, noble gases like argon inherited from Venus's formation. The concentrations vary slightly with altitude and location, but the overall composition is understood and stable until materials from 3I Atlas integrate into this system. Suddenly, Venus's atmosphere contains molecules it hasn't processed in billions of years. Hydrogen cyanide appears in concentrations elevated above background levels. Water vapor increases locally where the comet's materials were captured. Nickel compounds, which have no business being in Venus's clouds, are now circulating in the upper atmosphere. These aren't equilibrium components, they're perturbations. They don't fit into the existing chemical cycles because they didn't originate from Venus's geology or photochemistry. And when non-equilibrium chemistry enters a system that's been stable for billions of years, the system responds. It reacts. It tries to incorporate the new materials or break them down into components it can process. The sulfuric acid clouds that have been Venus's defining feature are now hosting chemistry they've never encountered. Water mixing with sulfuric acid dilutes the acid concentration locally, creating zones where the chemical environment is less aggressive. Hydrogen cyanide hydrolyzing into ammonia creates basic compounds, bases in an overwhelmingly acidic environment. Ammonia neutralizes acid. It forms salts like ammonium sulfate, which are stable and can persist for weeks before other processes break them down. Nickel ions dissolving into droplets give those droplets catalytic properties they didn't have before. Organic molecules produced from hydrogen cyanide breakdown accumulate in regions where photochemistry hasn't yet destroyed them. This is no longer the Venus atmosphere of early November 2025. It's a slightly different chemical system, perturbed away from equilibrium, actively exploring reactions and pathways that don't occur during normal operations. The changes might be small in absolute terms. We're talking about parts per billion concentration increases for most of these materials. But in a system as chemically active and dynamic as Venus's upper atmosphere, even small changes can propagate. They can create cascades of secondary reactions. They can produce compounds that wouldn't normally exist, which themselves go on to react with other atmospheric components. The atmosphere doesn't simply absorb the new materials and return to normal. It processes them, transforms them, and in doing so, temporarily becomes a different chemical system. And understanding what that different system looks like, what reactions are occurring, what products are forming, how long the perturbation persists, requires the data that's currently being analyzed from Akatsuki's observations during the encounter. We're waiting for confirmation of what theory and chemistry tell us must be happening. But the framework is clear. Venus received materials from outside its closed system, and those materials are now driving chemistry Venus hasn't experienced in geological timescales. Let's be specific about the chemistry that arrived at Venus on November 3rd, because precision matters when we're discussing atmospheric changes at this scale. By early November 2025, 3I Atlas had already passed its closest approach to the Sun. Perihelion occurred on October 29th, and the comet was beginning its recession back toward the outer solar system. But receding doesn't mean dormant. Comets remain active for weeks or months after perihelion as solar heating continues sublimating ice from the nucleus. The rates decline compared to peak activity, but they're still substantial. And the materials being ejected are the same suite of molecules and compounds the comet has been producing since August. Water, hydrogen cyanide, carbon monoxide, and the unexpected component that makes this story so remarkable. Refined nickel separated from iron through natural processes that mimic industrial chemistry. Water was still flowing from the comet at rates around 120 to 130 metric tons per hour by early November. This represents a decline from the peak rates of 140 plus metric tons per hour observed in October, but it's still an enormous mass flux. For comparison, a commercial jetliner weighs about 180 metric tons fully loaded. 3I Atlas was ejecting the equivalent of a jetliner's mass in water every hour and a half. Most of this water escapes into space, spreading outward in the comet's tail and coma. But when the comet passes close to a planet with sufficient gravity and a substantial atmosphere, a fraction gets captured. Venus's capture efficiency depends on multiple factors: the relative velocities of the comet and planet, the angle of approach, the density of the comet's coma at Venus's distance, and Venus's atmospheric interaction cross-section. Models suggest capture rates between 3 and 10% for materials in the vicinity during the encounter window. Apply that to the water flux, and Venus received somewhere between 3 and 12 metric tons of water spread over the several hours when the comet's influence was strongest. That might not sound like much compared to Venus's total atmospheric water content, which is measured in thousands of metric tons. But distribution matters. This water didn't arrive uniformly across the planet. It arrived at specific locations where Venus's geometry during the encounter placed its atmosphere in the comet's outgassing stream. Local concentrations at the arrival points would have been significantly elevated enough to create measurable changes in humidity, cloud droplet composition, and reaction rates for processes that depend on water availability. Hydrogen cyanide continued its remarkable exponential increase through October. By the time perihelion occurred on October 29th, HCN production had reached approximately 75 to 100 grams per second, based on extrapolation from earlier measurements. This is extraordinary for a comet. Most comets produce HCN at rates of a few grams per second, even at peak activity. 3I Atlas was producing orders of magnitude more, suggesting unusual composition or unusual sublimation processes driven by the comet's interstellar origin and the extreme temperature changes it experienced approaching the Sun after billions of years in cold storage. By November 3rd, during the Venus encounter, HCN production had stabilized around 80 to 85 grams per second. Over a 4 to 6 hour encounter window, the period when Venus's gravity and atmospheric capture were most effective, that translates to roughly 1.2 to 1.8 kilograms of hydrogen cyanide delivered to Venus. Hydrogen cyanide is not a normal component of Venus's atmosphere. It exists in trace amounts produced through photochemical pathways, but concentrations are negligible under normal conditions. The arrival of kilograms of HCN represents a genuine chemical novelty, and unlike water, which Venus's atmosphere already contains and knows how to process, HCN brings chemistry. Venus's system hasn't dealt with in its current atmospheric state. HCN is a precursor to amino acids. It's a building block for nucleotides. It's one of the key molecules astrobiologists look for when assessing prebiotic potential. And it just arrived at Venus in concentrations high enough to create localized environments where HCN-driven chemistry can proceed before photochemistry destroys it. Carbon monoxide was also being ejected at rates comparable to HCN, somewhere in the 60 to 70 grams per second range, based on spectroscopic signatures detected by ground-based observatories. Over the Venus encounter window, that's roughly 0.9 to 1.7 kilograms of CO arriving. Carbon monoxide exists in Venus's atmosphere naturally, but at concentrations around 20 parts per million. The comet's delivery temporarily increases this locally, creating enriched zones where CO concentrations are elevated above background. This matters for specific chemical reactions, particularly catalytic processes, where CO acts as a reactant or substrate. And then the nickel. The refined nickel that spectroscopic analysis revealed was being ejected preferentially separated from iron, an anomaly that suggests the comet underwent processes resembling the industrial Mond process, where nickel forms volatile nickel carbonyl compounds that separate from non-volatile iron. By November 3rd, nickel ejection rates were likely in the range of 3 to 4.5 grams per second, slightly declined from the peak rates observed in October. Over the encounter window, that's 50 to 110 grams of nickel arriving at Venus. This is a tiny mass compared to atmospheric scales, but nickel's chemical significance far exceeds its mass. Nickel is a catalyst. It accelerates specific reactions without being consumed. Even trace amounts can have disproportionate effects on chemical systems where those reactions are occurring. When nickel arrives at Venus and encounters sulfuric acid, it doesn't remain as metallic nickel. It reacts immediately. Nickel dissolves in sulfuric acid, forming nickel sulfate, a soluble compound that integrates into the liquid droplets. Those droplets, now containing nickel ions, gain catalytic properties. Reactions that would proceed slowly or not at all in pure sulfuric acid can be accelerated when nickel is present. The water-gas shift reaction carbon monoxide plus water-producing carbon dioxide plus hydrogen is catalyzed by nickel. Fischer-Tropsch type reactions that build longer carbon chains from simple precursors can be catalyzed by nickel surfaces. Venus's sulfuric acid droplets have just acquired an ingredient that enables chemistry they couldn't perform before. Beyond these major components, the comet was delivering a suite of minor species, organic compounds synthesized in the coma through reactions between HCN, water, and other molecules, sulfur-bearing compounds from cometary dust, silicates and mineral grains, trace metals beyond nickel. The complete compositional inventory wasn't documented because spectroscopy prioritizes the most abundant species with the strongest signatures. But comets are chemically complex, and everything the nucleus releases becomes part of the delivery package. Venus received not just pure water and HCN, but a mixture, a chemical cocktail containing dozens or hundreds of distinct molecular species, all arriving simultaneously, all beginning to interact with Venus's existing atmospheric chemistry the moment they're captured. This represents fundamental novelty. Venus's atmosphere hasn't received an external chemical delivery in billions of years. The materials now circulating in the upper cloud layers are genuinely foreign. They didn't originate from Venus's surface or from photochemical breakdown of atmospheric gases. They came from outside, from an object that formed in a different star system, traveled through interstellar space for eons, and happened to pass through our inner solar system at precisely the right time and trajectory to intersect Venus. The chemistry that arrived carries information about cometary processes, about interstellar conditions, about chemical pathways that operated during the comet's formation billions of years ago. And now that chemistry is interacting with Venus, being transformed by sulfuric acid and solar radiation, producing compounds that blend interstellar heritage with Venusian processing. By late November 2025, the initial arrival has passed. The materials are now integrated into Venus's atmospheric circulation. They're reacting. They're being broken down and recombined. They're creating a temporary chemical state that Venus hasn't experienced in geological memory. And the data documenting this transformation exists, recorded by Akatsuki during the encounter and transmitted back to Earth, waiting for analysis to reveal exactly how Venus's chemistry responded to this unexpected gift from interstellar space. Understanding where the comet's materials ended up in Venus's atmosphere requires understanding how Venus's gravity and atmospheric dynamics capture and redistribute incoming matter. This isn't like dropping objects onto a solid surface where they stay where they land. Venus's atmosphere is a fluid system, constantly circulating, constantly mixing materials vertically and horizontally. When materials from 3I Atlas entered Venus's sphere of influence, they didn't simply fall straight down. They were captured, decelerated, and integrated into atmospheric flow patterns that immediately began carrying them away from their initial arrival points. The distribution of these materials across Venus's atmosphere determines where the highest concentrations exist, where the most active chemistry is occurring, and where spacecraft instruments are most likely to detect the changes. Venus's gravitational sphere of influence, the region where Venus's gravity dominates over the Sun's, extends roughly 1 million kilometers outward from the planet. This is a substantial volume of space, and when 3I Atlas passed at 97 million kilometers distance, portions of the comet's
Okay.